Good afternoon, everyone. My name is Mehdi Khanzadeh. I'm assistant professor from Temple University. Today I'm going to basically discuss the application of cellulose nanomaterials in 3D printed composite system for mainly architectural applications. I would like to thank you, my student Abdullah, Garrett, and Nathaniel. They're interested in work on this. So here's the motivation for our study. As we know, 3D printing is getting more popular for different applications, but the system we are using for 3D printing, low water binder systems, right? A lot of cement. It's not cost effective. It's not sustainable considering the initiative we have currently. We were thinking to use this cellulose nanomaterial, which are a green material, in the 3D printed system to improve both fresh properties or printability and also the mechanical performance, which I'm going to discuss. And the other part of this study, kind of novelty application of this material in alkali activated binders. So objectives, as I said, developing the mix design using these cellulose nanomaterials and looking at the impact on the printability and harden properties. And also our collaborator from University of Wisconsin-Madison, they're basically using this as the input information from our experiments for techno-economic analysis to see if this is feasible or not. So the background about the cellulose nanomaterials, mainly we use the CNCs or cellulose nanocrystals in this study. Also, some other people use the CNFs, the cellulose nano fibers in the concrete, mainly in the mold concrete, traditional concrete. So these are crystalline part of the cellulose, typically extracted through the hydrolysis process using acids. The size, as you can see on the let me see. Here on the upper right side, the width around few nanometer, the length around 50 to maybe 100 to 100 nanometer. So the large benefit from this use of the CNCs are they are renewable materials, they are biodegradable, they are sustainable. Currently, even they've been used in the cosmetic industry or in food industry. So they are very safe, and we have them in high quantity in the nature. So these are really great benefits from use of these materials. So here are research scopes. I'm going to discuss how we design the mixes, the impact on the fresh properties, and then performance. So as we know, there are some challenges for developing the mix design for 3D printing compared to traditional concrete, obviously. Considering our limited experience with this. For extrudability and printability of these systems, we consider these parameters. Basically, the extrusion consistency, we use the extrusion pressure. So as you can see at the top right side, we use a similar system as Narian discussed. Basically, this syringe system, by changing the RAM or displacing the RAM, we can look at the pressure, how it changes over the print time. The splitting and tearing, obviously you are familiar with this, right? This is not a acceptable system. And regarding the buildability, we looked at how many layers we can stack. Since we were interested to print 2-inch by 2-inch geometry, so we printed around 11 layers. And if we didn't see extensive deformation, then that was acceptable for us. And also in some system, we saw excessive water leak from the nozzle due to the separation of the material. So that wasn't the printable system either. So based on those criteria, we developed these 8 different mixes. At the top table, you can see the OPC mixes controlled without CNC, and then different percentage of the CNC by volume of the cementitious material. At the bottom, you see the alkali activated system, again, control and different CNC proportions. In case of the alkali activated binder, we use the mix of flash, classic flash, and slag. So 70% flash and 30% slag. Again, I'm going to discuss how we come up with that number. The CNC were in aqueous suspension around 11% solids. And for the activator, we use the combination of a sodium hydroxide and sodium silicate. This is our printing setup. At the left side, you see the printer. We designed the printer in a way that we have a plug-in system. Basically, we can plug off easily, load the material, consolidate it, and put it back. So this gives us a lot of flexibility in the open time, right? So it extends our open time. So here you see the example of the printing. As I said, 2 by 2 by 7 inch. So we can cure them, we can cut them for compression or flexural experiment. So after printing, and regarding the pattern of printing, we use this, basically the outer or perimeter layers is more straight line. The infill is more zigzag. And the main reason for this basically we got better dimensional stability from this pattern. So after printing, we cure the sample, the OPC system, 28 days inside the water or the calcium hydroxide solution. For the alkali activated system, we adapted 2 different types of curing. The first method, we seal cure them for 28 days. The other method, we heat cure them at 60 C for 7 days. Regarding the basically fresh properties, this is the what I'm showing at the right side here. Here, the x-axis is the CNC dosage, the y-axis is the required liquid to solid ratio to be printable. So as you can see, for alkali activated system, we need more liquid to binder ratio to be printable, but for OPC lower. But something we notice, after 1% CNC use, we see this higher exponential increase in the case of the OPC, and we're seeing that's the critical point to reach that agglomeration and aggregation of the CNC and OPC system. Regarding the pressure, I mentioned to look at the consistency. So this is the example you are seeing here. We have alkali activated without CNC, with CNC. So the use of the CNC lowers the pressure a lot, and this works as a viscosity modifying agent as well as the high range water reducer in the alkali activated systems. Here's how we developed the alkali activated mix design. So you see the combination of the basically activator as well as the change in the composition of the binder. So we looked at which portion is printable, which portion is printable with retarder, and where's the optimum mix. So you can see that here. And if we look at this by that pressure graphs, so you see non-printable system at the left side here, right? So this very high pressure requirement, and you have this hard time to basically extrude this through. And at the right side, these are the optimal mixes I mentioned. Regarding the mechanical performance, by inclusion of the CNC, this is the modulus of the rupture versus the CNC dosage. So up to a certain percentage, again, we see an increase in the flexural strength or the MOR of this system by use of the CNC. By using the heat cured for the alkali activated, we see much more improvement, the black dots you are noticing here. The other point here is we have to notice that the reduction at that higher percentage is part of it because of the we are using a higher water binder system, so that's basically reducing the mechanical performance. This is the compressive strength versus the flex or MR, right? And we compare with the ACI equation, so you can see the heat-cured alkali activated is very ductile system, even if it's performed as a high-performance concrete. And that's a CNF mix we tested. Even CNF mix with a 0.1%, it showed very promising result, 30 to 40% increase in the modulus of rupture. We looked at the porosity of this system. There's a strong linear relationship between the compressive and porosity. The electrical resistivity, we saw some abnormalities, and we think this is mainly due to the leaching of the alkalis from the reacted unreacted phases in the system. So that's why we are seeing a higher electrical resistivity for alkali activated versus the OPC. The other interesting observation we had, the internal curing effect from the CNCs. So when we are looking at the bound water over the depths of the samples, we are noticing in OPC system there is a increase in the degree of hydration. So this can be really helpful in 3D printed system when we have lower permeability, right? The external curing effect is limited, or the depth is limited. So this is an interesting observation we had. But in case of the alkali activity, there's no impact on the reaction, which was understandable. I'm going to skip this one. We looked at the SEM images after the flexural experiment. So at the left side, alkali activated seal cure, right side, alkali activated heat cure. So you see a lot of cracking in case of the seal cure, which makes sense, right? We have low strength for the seal cure one. And the main reason we observe here is due to the heat curing, we get higher dissolution of the flash particle as well as the slag particles, and we get more cohesive and uniform structure. So even unreacted flashes or slags are embedded inside that matrix, so that helps to improve the strength of the system. This is an observation again from EDA Explorer, the main product. So at the upper picture, you can see a lot of unreacted flashes from in seal cure versus the heat cure, which is minimal. So as I said, we introduced some of this as a for input as a for techno-economic analysis. So I'm going to skip this one due to the time limit. So these are the conclusion. CNC can help to improve the printability of our alkali activated and OPC system, works as a VMA, and also CNC improves the mechanical performance and the internal curing effect, and finally the sustainability part, right? It can really work as a sustainable system. So with that, I thank you for your attention.